Assalamualaikum and hi to Dr. Hamdan and my friends. Today our group will be presenting about the derivation of variable fluid temperature with countercurrent operation. So these are our group members. First is myself, Muhammad Hasman bin Muhammad Snin. Next is Lu Jinglin, Chin Jo Zien, Chong Wan Sing and Nur Arina Hanis. So for the countercurrent flow operation, the reacting mixture and coolant flow is in opposite directions. As we can see here in the figure 12.4, at the reactor enters, V is equal to 0. The reactant enters at temperature T naught, which is here, and the coolant exits at the temperature TA2, which is out here. Okay, and at the end of the reactor, the coolant enters at the TO, T naught, and the reactants and product exit at the temperature T. So for the derivation of variable fluid temperature, first we must do the energy balance on the coolant in the volume between V and V plus delta V. This is the formula, as you can see here. The rate of energy minus the rate of energy out, and then plus by the rate of heat added by conduction through the inner wall. The rate of heat, we can use this formula, which is UA times TA minus T times delta V, which is TA is the coolant temperature and T is the temperature of the reacting mixture in the inner tube.
For the second step, we rearrange the equation from the first step. And then we make the delta V equal to 0. So we get this equation. Negative MC this HC over dV plus UA Tm minus T equal to 0. The MC is the mass flow rate of the coolant. And then analogous to equation 12.4, we get this equation. And then we make the I to become C. The C is coolant. And then we get this. This one is the change in enthalpy of the coolant. And then now we do some maths. If we move this UA Tm minus T to the right hand side, we get negative UA Tm minus T. And then we divide this by the negative MC. So we get the HC over dV equal to UA Tm minus T over MC. And then we divide both sides by CPC. And then we get the HC dV CPC GHC over dV times CPC equal to UA Tm minus T over MC times CPC. So now from here we know that DHC over dV equal to CPC dTA over dV. So we can equate these two equations, and then at last we get this equation as our energy balance. So at the entrance, when our volume equal to 0 and conversion equal to 0, our TA, coolant temperature equal to TA2. TA2 is the temperature where the coolant exits, and at the exit when V equal to Vf, the final volume, our TA is equal to Tn naught. Tn naught is the temperature where the coolant enters.
So for this slide, we will explain the procedure solving for the exit condition for PFRs with countercurrent heat exchanger. Solution to a countercurrent flow problem to find the exit concentration and temperature requires a trial and error procedure. So first, consider an exothermic reaction where the coolant stream enters at the end of the reactor, which V equal to Vf, at a temperature Tn0, say 33,000 Kelvin. We have to carry out a trial and error procedure to find the temperature of the coolant exiting the reactor. Second, assume an exit coolant temperature at the feed entrance which X equal to 0, while V also equal to 0, to the reactor to be TA2 equals to 340 Kelvin, as shown in figure 12.5a. Next, use an ODE solver to calculate X, T, and TA as a function of V. Then we can see from figure 12.5e that our gas of 340 Kelvin for Ta2 at the feed entrance, which V equal to 0 and X equal to 0, give an entering temperature of the coolant of 310 Kelvin, which V equal to Vf, which does not match the actual entering coolant temperature of 300 Kelvin. Now, guess the coolant temperature at V equal to 0 and Z equal to 0 of 330 Kelvin. We see from figure 12.5b that an LZ coolant temperature of Ta2 equals to 330 Kelvin will give a coolant temperature at Vf of 300 Kelvin, which matches the actual Ta0. So that's all from us. Thank you and stay safe.